Hey everybody, we're going to go ahead and get started here with our next talk. Introduce Jack McGinnis. He is a vulnerability researcher at Interrupt Labs. Jack is based in Denver. He's a vulnerability researcher on the Android team there. He's in North Carolina and originally from Greensboro, and he attended Georgia Tech, where he studied computer science. Professionally, he started his career as an IoT pen tester, focused on medical devices before making the transition to do vulnerability research full-time. Outside of work, Jack competes in middle-distance triathlons and enjoys being on a snowboard as much as possible. So, yeah, welcome, Jack.
Thank you. Awesome. Thank you, guys, and thank you to BSidesRDU for having me out. So as mentioned, my name is Jack McGinnis, and if you found yourself in this room, we will be talking about hacking the FiiO M6. In particular, I'll be talking about a local privilege escalation vulnerability I found and exploited, which was given the CVE 2023-30257. So just a brief agenda for today's talk. I'll first do a little bit of an overview of myself. We just had one, so I'll try not to spend too much time on it. And then I will go into kind of a description of the FiiO as a device, both from a consumer standpoint as well as from a technical standpoint. After that, I'll talk a little bit about vulnerability research, the methodology I used to attack the FiiO M6, and what bug actually ended up shaking out. We'll go through a quick root cause analysis of that bug before talking about the overall exploitation strategy. And finally, ideally, if there's still time, I'll open it up for questions if I've left anything unanswered. So brief overview. Again, I'm a vulnerability researcher at Interrupt Labs at the moment. Legal caveat with that all of this was done on my own time, and I don't speak for my employer, so nothing here is a reflection of their views. I'm also at _Stigward on Twitter or X, for those of you who still use the platform. And so feel free to reach out on there if you want to talk vulnerability research or if you have any additional questions after this. I'm also a first-time speaker, so fingers crossed that this goes well. And again, thank you to BSides for letting me demo this. So general goals for the presentation today, first and foremost, I hope that everyone's able to walk out of this room understanding what the FiiO M6 is, what the bug identified was and why it was there, and how we ended up exploiting that. More generally though, if you've never done any kernel exploitation, if you've never played with an Android device before, I'm hoping that this kind of serves as a place to get your feet wet and maybe a primer in that area. So we'll touch on everything from kernel exploitation 101 to the overall vulnerability research methodology. And so hopefully if you are a CTF player or a beginner in the VR space, this will be a good talk to kind of not only inspire confidence, but kind of prime you to go pick up a device yourself and start hacking on it and just learn as you go. So getting into the actual content, the FiiO M6, what is it? So this is a portable high-resolution music player. And basically, it's a glorified MP3 player is what you need to know for this talk. It's geared towards the audiophile, the person who likes to take high-resolution audio on the go and drive some higher-powered headphones. But under the hood, it's really just an MP3 player. It was released in 2018. And it was discontinued in 2022. Both manufacturing was discontinued as well as software support. So it's not receiving any updates at the moment. What'll be a little bit more interesting for this crowd is what it runs under the hood. And so what I alluded to earlier is that this is an Android device under the hood. It runs a very customized version of Android 7. Which by today's standards is fairly outdated. We're going on Android 14 now, so that Android version was based on Linux version 3.18.14. Again, fairly outdated by today's standards. The actual device is based on the Exynos 7270 chipset. That's not going to be overly important for the research presented here today, but what is important is noting that that's an ARM64 based CPU. And so all of our exploitation or reverse engineering, anything we cross-compile for the device, is we need to take into account the fact that it is ARM64. The last part here is the firmware version. So the bug is in firmware version 1.0.4, which was released May 20th, 2020. This is also the most up-to-date firmware version. So if you buy the device today, you can still root it using this methodology. I guess as a slight detour into a note on ethics, this vulnerability doesn't have any remote capabilities, and there's no Google Play services on the device or anything like that. So the purposes of disclosing it to FiiO and then to telling it here to you today is really just so that people can take control over the full device that they own. But this doesn't give any sort of primitive to a remote attacker. So jumping into the vulnerability research and discovery section, I first want to start a little bit with Android debugging, just to make sure that everyone here has a baseline context for the environment we'll be operating in. And so Android devices come with the capability of enabling USB debugging just through the GUI in the settings menu, as if you were turning on and off Wi-Fi or something like that. And what this allows you to do is send commands from your computer over USB to your device, your phone or your MP3 player. In particular, Android produces this tool called Android Debug Bridge, or ADB. And ADB is a tool that works in your command line, and you can send commands to your device. The most important command, and the one we'll be most interested in, is ADB shell, which literally drops you directly into a shell on the device as a low privilege user. So we have the ability to plug our device into the computer, drop into a shell, and we are a low privilege shell user just right from the tools provided by Android. And so what we're actually interested in is taking that shell access and escalating our shell from that shell user to a root shell on the device. The question then becomes, okay, how can we have the kernel process untrusted user data from our shell user? And how can we leverage that into a potential vulnerability and exploit? And there are a number of different answers to this question, but the one that I chose to pursue and the one you most often see are kernel modules and kernel drivers exposing files to user land processes. And so you've probably heard the common nomenclature that everything on Linux is a file. And so kernel drivers, which run in kernel land, expose these files to user land, and you can perform file operations on these files. And the handling for that input actually happens in kernel land. And so to hopefully concrete this idea a little bit, and this might be really low resolution, but hopefully you can see it. This is an example kernel driver that I mocked up for the purposes of this presentation, just to kind of solidify what I just talked about. And so at the bottom here, we have a character device being registered. So this is an initialization function, and we see the first line of that function has a registered character device. In particular, we're registering it with the device name defined at the very top. Example underscore device. And so this creates a new entry in the dev file system, or on the Android file system, in /dev/example device that this kernel module is now in charge of controlling. And so if our shell user has permissions to operate on that file, we might do something like perform a write operation. So we'll open /dev/example device, we'll get a file descriptor, we'll write to it, and then the kernel module is in charge of actually handling that write operation. And so in this case, it defines this file operations struct, and it says for all write operations, we want to forward those to the dev_write function to be handled accordingly. And so what we're looking for this kernel escalation vulnerability, or this privilege escalation vulnerability, is we're looking for a vulnerable handler that parses our untrusted data in a kernel module that we might be able to exploit and then, in turn, escalate our own privileges as the shell user. So zooming out kind of 1,000 feet as just a very basic diagram, on the left here, we have our shell user. We're literally writing the data, some data in this case, to /dev/example device, and that string will be processed by the dev_write function that was demoed previously. And so I want to talk a little bit about the very sophisticated dumb fuzzing method I came up with to go about kind of looking at each of these handlers. And so this is the previous diagram that you saw previously, and kind of what I mentioned was you would actually, in order to find a vulnerability, you would need to reverse engineer all the kernel modules. You would need to see what files they expose. You would need to see which of those files your shell user has access to, and then you would actually need to find a vulnerability in one of the handlers. And personally, that sounded like a lot of work. And so instead, what I did was the following. I came up with I borrowed a fuzzer that essentially enumerates the entire file system. So you push the binary directly onto the device, it enumerates the entire file system, and just every single file that it has access to, it's going to open, cram some garbage data into it, and see what happens. That is the entire fuzzer. And again, I didn't even come up with this, as sophisticated as it is. This was originally published by Gamozo Labs, and he called it the world's worst Android fuzzer. And I would happen to agree, but it does work. And he mentioned that he had hits on pretty much everything he ran it on under Android 8. And this ended up being successful for me as well. And so what you see here is another low resolution shot of our fuzzer's running, and we see that it starts to write to proc ftxxxx debug, and then all of a sudden the device crashes, we get kicked out of our fuzzer, and we're back in our host machine, this Ubuntu box I was using for testing. And so at this point, I'm thinking, okay, there might actually be a bug in ftxxxx debug in procfs. And so I wanted to try and root cause analysis that bug. And unfortunately, FiiO does not release the source code for their device, but it had a unique enough name that I just kind of started Googling around, and I ended up finding the corresponding driver or a very similar driver in the Zenfone 2. And so in particular, they do release their source code, and we see that they're registering some procfs file operations here. And we have a write handler for this ftxxx debug called ftxxx debug write. And so this is the handler for that function and where we can actually see our bug. Some of you might see it right away, but I'm going to kind of break it down step by step. So these write handlers do always take the same 4 parameters. The 2 that are attacker controlled and the 2 we're interested in are the buffer parameter and the count parameter as outlined here. Buffer is always going to be what we're writing. So if we write 4 A's to our exposed file, buffer is just going to contain 4 A's. And count is going to be exactly what it sounds like. It's going to be the derived count of that buffer, so 4 in that case. This function initializes a fixed-based stack buffer of size FTS packet length, and then it also copies our count parameter into a variable called bufflen. We can see in the header file that FTS packet length is of size 128, and then it just does a straightforward copy. And so it's copying our attacker controlled buffer, our user land buffer, into the kernel buffer of size bufflen, but it has no size checking. And so as long as our count or our buffer is greater than size 128, we're actually going to overflow this kernel buffer, and that's where our crash originated from. And so after playing with it a little bit, I ended up being able to determine the offset and create a kind of a straightforward crash POC. So in this case, what you're seeing is I'm writing, at the top part is the actual code. I'm writing 1,024 bytes of just junk OX41s, and then I'm writing 8 bytes of OX42s. And you see in the bottom, the PC gets set to OX424242, indicating that we've actually directly overwritten the saved return address, and we have full PC control at this point. The other part about this is nowhere in here do you see it complaining about a stack cookie or anything like that. So there's just straight up no mitigations on the device, and we have overwritten the buffer, and we now have PC control. So at this point, we found a bug, we have a straightforward bug, and we can move on to exploitation. Again, I want to do a brief aside into kernel exploitation 101, just to make sure everyone's kind of on the same page. So if you come from a Linux userland background, or you've done some CTF challenges, you might have tried to pop a shell, use it in a pwn challenge or something like that. Obviously, when you're doing kernel exploitation, the tactics and techniques differ because you already have a shell, and the goal is just to escalate your privileges. In this case, one of the best documented and well-known techniques is one where you use these two kernel functions, prepare kernel creds and commit creds. And so prepare kernel creds, if you call it with a null argument, will always return a pointer to a root credential. And then commit creds will always take a pointer to a credential and commit that to the currently running process. So if you call them one inside the other, as you see kind of the third blue line down there, the internal function call, the prepare kernel creds, will return a root credential, and then commit creds will push that to the currently running process. The other really nice thing about the FiiO device, nice in the sense of attacker aspect, is that it has publicly available firmware ready for download, and we can actually extract symbols directly from it. So you're able to unpack the firmware, grab the kernel image, and then run a Python script against it and grab some of the symbols. So we see the two functions we need. Also, while I was doing triaging of each of the crashes, I noticed that most of the addresses don't ever change. And I did end up confirming this, and so we can confirm there's no kernel ASLR at this point too. So another place where a mitigation maybe would have stopped this attack or needed another bug, but in this case, it wasn't there. And so we can just hard code these addresses directly into our exploit. The last thing we want to talk about here is exploit strategy. So we have the functions we want to call, we have the primitive, what do we actually want to do now? And so initially I set out to write a ROP chain. It's only two function calls. This should be a pretty straightforward ROP chain. Unfortunately, I didn't have a debug shell because I didn't have a root shell at all, so there was no way to debug the device. And so I was just doing crash-based debugging, where I was intentionally crashing the device after each call in the ROP chain, and then checking the register dumps and the PC and the state of everything, and trying to determine where I was in my chain, what was happening, etc. As I did that, I noticed that the bottom of the chain started to flow into X21, which is just an ARM64 register. And X21 was a pointer to the stack, and we start to have attacker-controlled data at that area of the stack. And so I was like, you know, we haven't had a single mitigation yet, so what are the chances the stack is executable? And so the new theory I had was, what if we overflow our stack, our function, we overwrite our saved X30 address with a single ROP gadget, and we just tell it, hey, branch execution to X21. And then X21, as we just showed, now contains more attacker-controlled data. So what if we turn that data into shellcode? And so this became a more complicated ROP chain to a one-shot ROP chain to potential shellcode. This is just a demo right here showing that I was able to find a ROP gadget pretty easily. I'm not going to detail how that works, but I think I used Ropper or something. And here we're just showing that X21 and PC are the same address. The way I confirmed, or how I went about trying to confirm execution on the stack, was by just writing a bunch of nops to X21. And so the idea there is our PC and X21 after the ROP gadget are going to be the same address. And if PC starts to execute the nops, it's going to start sliding down the nop sled. And then once it eventually crashes, there'll be different addresses. And so that's what this screenshot shows. And so at this point, we've confirmed, hey, we can actually slide down this nop sled, which means that we have code execution on the stack. The stack is executable. And everything from now on should, in theory, be custom shellcode. This is where I thought it was game over. It wasn't quite, so stick with me for a second. But this executes on the strategy we talked about earlier. So you can see the first instruction is just moving a null argument into X0, which is argument 1 in the ARM64 calling convention. Then we branch to prepare kernel cred. That comes back. The return value is also stored in X0 in ARM64, which is nice for us because we don't need to move our return value. And then we branch to commit creds. And so now, theoretically, our shell code has successfully escalated the privileges of our running process. This is where things start to get a little bit funky. remember, we're in kernel land right now. The CPU is in supervisor mode, and we're writing custom shellcode. And so we need to somehow figure out how to switch the CPU back to unsupervised mode and return execution back to user land in the script that kicked this all off. And ARM doesn't really document that process very well. And so I just kind of made some stuff up in hopes that it might work. And so what I did was I basically stored a function pointer to our exploit script on the stack and just grabbed that. And then I also stored a fake stack pointer on the stack and grabbed that. And then I manually set these system registers. So I set EL0 to the stack pointer, which is what the calling convention says it should be. And then I set EL1 to the return address in user mode. So the idea here is, hey, we're resetting everything for user mode. Here's the user's stack. Here's the user's return address. And then we run ERET, which should kick us out of supervisor mode and return us back to our exploit script. Unfortunately, this is not the type of segmentation fault you want to see when you're doing vulnerability research. This is a segmentation fault in my exploit script. And so what ends up happening is we do return from supervisor mode. We do get back to our user land process. I actually even get the win function to be called. But then immediately after that, anything you try and do causes a seg fault. And it's almost guaranteed to be because of the super ugly way I'm trying to reset the state of the device prior to returning. But after a full week of trying to debug this and trying as many different things as I could think of, I kind of just stepped back and decided, let's just revise our strategy a little bit. And so at this point, to recap about what we do actually have. So we have the ability to execute arbitrary shellcode in kernel land, in supervisor mode. That should be enough. We also, what the previous screenshot showed, is we can return to user land without crashing the device. So all the operations we performed in the kernel actually did take place. We just didn't, we weren't able to successfully inherit the privileges that we gained. And so that's a huge win because we're not kernel panicking, we're not rebooting the device. What we don't have is the ability to directly escalate our currently executing processes privileges without crashing. And so what can we do? And after trying to combine all of those buzzwords into a single Google search, I came across the hot plug eater attack, which was originally presented in 2016. And essentially, this attack, I wish I had found it originally. The idea is there is a global variable in the kernel, which remember, we have all of the variables in the kernel at static addresses, so we can find it very easily. It points to a script. So event helper points to a script, and that script gets executed on hot plug events. So when you plug in the phone, when you plug in a keyboard to the bottom of the phone, this hot plug event happens, and whatever event helper points at gets executed by the kernel. The part that gets interesting is just simply changing event helper is enough to kick off that script. So if event helper points at script X and all of a sudden I change that event helper to point at script Y will be run by the kernel when the change happens. So you don't actually need to plug the phone in order to get it to kick off. And so with this, we can actually use this idea and our previous exploit and kind of combine them. And so what we're going to do now is we're going to create a malicious script in the globally readable and writable directory on Android data local temp. And then we're going to trigger an overflow and ROP to our shellcode. Except for this time, our shellcode, instead of doing the prepare kernel creds, commit creds strategy, it's just going to overwrite event helper with the string data local temp and then whatever the name of our malicious script is. Then it's going to segfault. We don't care about it anymore. It's going to return to userland and it's not going to continue execution because what it's done in the kernel is enough for our purposes. And then once we change event helper, ideally the kernel is going to go ahead and execute that malicious script we've pointed event helper at, and we will ideally inherit root permissions. This is a screenshot of kind of that whole thing being wrapped into a singular bash script. And so what you see at the top is we create a new file called data local temp cmd. Cmd just is a simple command that tells whatever's executing it to forward a shell on port 4444. And so ideally, when the kernel executes this, it will forward a root shell on port 4444. Then below that, on line 7 and 8, we actually run our binary exploit, which is doing that ROP and overriding uEvent helper. We're piping that to dev null because we know it's going to segfault, but we don't really care. And then we sleep while that takes place. And then we launch a listener on port 4444. So once that script actually gets changed, that uEvent helper points at, it will forward a shell to our listener. And this is kind of what that looks like. So you can see at the top, I am the shell user. I run the exploit. It goes through each of those steps that we just talked about. And by the end, it is we're the root user. Unfortunately, I'm an idiot and the device is still in Denver. And so we won't be able to demo this live, but it does work. And the full exploit code is on my GitHub, as well as I did a 2-part blog post that details this a little bit more in depth. So feel free to go check that out as well. And last but not least, if any of this is interesting, if you like C and C++ and Binary Ninja, we are hiring. So check out our website, interruptlabs.co.uk, or come find me during the conference, and I'm more than happy to answer any questions you have. I think I'm right up on time, but I'm happy to answer questions if there's anything you guys are curious about. Thank you.